right. Hi, everyone. Thank you for joining today's webinar. We are with Dr. Ernie Chan today, and we're very happy to have him back. Ernie is the managing member of QTS Capital Management, a commodity pool operator and trading advisor, and he is also the author of Machine Trading, Algorithmic Trading, and Quantitative Trading, as well as a popular financial blogger at epchan.blogspot.com. Thanks, Ernie.
Thanks, Paige. Thanks very much for inviting me again to give this webinar, and thanks everybody for attending. So the topic I have chosen for today is what to do before machine learning. So machine learning has advanced to such a stage that practically any high schooler who knows some programming can now run random forests or a deep neural net model on any data that you throw them their way. It's not difficult. Just a few lines of code will enable you to create a neural net, LSTM, whatever style architecture model that you like, using one of the standard packages. So it's actually very trivial if you look at it that way. But if that's the case, what is your value add? What is our what can we do to distinguish ourselves, to get an edge over all these other high school students? Well, what we are going to add value is actually not necessarily in creating the neural net or the random forest, or even in various types of hyperparameter optimization, all of which, by the way, nowadays can be automated to a certain extent. So you really have to do nothing with regard to the machine learning process itself. It is completely automated. So what we have to do, what we can add most value, is to set up the problem before the machine learning step, and also to utilize the results of machine learning in order to assist us in our task, which is, in my case, and perhaps in many of your case, trying to trade profitably in the market, right? So it is the before and after machine learning, I think, that is actually where most of the work and time that we have to spend on. The machine learning itself is practically completely automated, and I'm not going to talk about that today, actually, and I'm not also won't be talking about what's going on after, because that very much depends on what kind of application you're going to use it for. But what I'm going to talk about today is before you even start machine learning, what you have to do to set up the problem so that you can extract the most value out of machine learning. So there are, I think, three major steps that you have to do before you feed your data into any kind of machine learning algorithm. Obviously, the first step is to figure out what we are trying to predict. And that is actually non-trivial. We will explain more later. The second point, the second step, is that before you do machine learning, you should think about what a human can do. That is actually somewhat different for other machine learning problems, because other machine learning problem, like for example, deciding whether a picture is that of a dog or a cat, right? Well, the baseline strategy is a human determination. You can determine whether a picture is a dog or cat with probably 99.9999% accuracy if you look at the image, and so it's a no-brainer, right? So a machine learning algorithm in that case, it's very unlikely to perform as good as a human. Although now I heard it is approaching human accuracy in terms of a simple dog-cat categorization. But it's still a non-trivial problem, right? But in financial market, in financial machine learning, that is quite different. Even a human is not, it is not easy for a human to tell whether the spider is going to go up or down on the next trading day, right? If it is easy for a human, we would not need machine learning. We would all just sit back and watch ourselves becoming billionaires. But this task is by no means easy for a human. So what we can use machine learning to do is actually to compare a machine learning model with what a human can do, and I will explain exactly what I meant by human strategies, right? So in general, I call that benchmark or baseline strategy. It's what a human trader could hope to achieve. And in this case, it's very different from other kind of machine learning because the machine learning algorithm is supposedly should be able to do better than a human. That's quite different from what the Googlers and the Facebookers are used to. In financial machine learning, the algorithm is supposed to perform better than a human. And then, of course, the third step is actually fairly common to a lot of machine learning problems, and that is data and features engineering. But in financial machine learning, there are a lot of caveats and subtleties that we need to look at, and many of which are not just limited to machine learning problem. If you are a traditional quant trader, you still have to deal with those, but they are also equally important and perhaps more important than for machine learning algorithm. And I'm going to talk about some of them. And the subtlety involved in the data and features engineering for financial machine learning, I would say, is far exceeds what a machine learning algorithm is able to do outside of finance, with the possible exception of natural language processing. Because if you are familiar with natural language processing, you know that there are a lot of ways to standardize, to regularize the natural language data before you can feed it into a model. And in finance, there are equal, if not more, steps that are necessary to deal with the data and engineering the features. Okay, so so let's take it one step at a time. The first step: what are we trying to predict? Most of the time, when you tell someone that you're trying to use machine learning to trade stocks or whatever, trade some financial instruments, they would automatically think, oh my goodness, you're trying to predict returns. Is that spider going to go up or down? But that actually is the toughest problem that you can come up with in finance for machine learning to solve. It is tough because returns is what are subject to what some people call reflexivity. That's a term popularized by George Soros, but it's known in economics, before him. What it meant is that the action of making a prediction will change the outcome in the real world. And that is completely different, again, in nature for many of the other machine learning problem, maybe, except for maybe chess playing or something like that. But typically, when you are trying to predict, the weather, or whether you're trying to predict, disambiguate whether the picture is a cat or a dog, or to understand language, just because you understand or your machine learning model are accurate, will not change the outcome. But that is not the case in finance. If you are able to predict returns pretty accurately, well, very soon those returns will be arbitraged away, because believe me, you won't be the only one who will find that particular arbitrage opportunity. An arbitrage opportunity can be found by multiple ways. Some people find it by manual observation, others find it by machine learning, yet others find it by traditional quantitative methods, and so on and so forth. So this return label is going to be arbitraged away, and they are reflexive. So to use machine learning to predict returns is actually the hardest problem you can possibly create for yourself. But there are targets, there are labels in machine learning that are not subject to this reflexivity. As I mentioned, weather in the Midwest is one such a target. Now, you might, why would we want to predict weather in the Midwest? Well, if you can predict weather in the corn belt, and if you trade corn futures or soybean futures and whatnot, that could be quite useful. Similarly, if you can predict gasoline consumption, I would suppose that is useful if you trade gasoline futures or crude oil futures. Closer to finance, actually, if you can predict realized volatility accurately, realized volatility actually cannot be arbitraged very easily. You might think that, oh, well, why can't you buy options? Well, when you buy and sell options, what you're arbitraging is the implied volatility, but it's not the realized volatility. To delve deeper into why realized volatility is not a reflexive variable, I actually have given a talk at one of the QuantCon in back a couple of years ago. So if you go to the QuantCon video library, you will probably find the talk on volatility, the peculiarities of volatility. I had a full explanation of why it is that realized volatility is not something you can easily arbitrage away, even if you can predict it very accurately. And so, therefore, realized volatility is a good target for machine learning. Now, of course, there are traditional methods like GARD to predict realized volatility, and they're doing a pretty good job already. But again, when you apply machine learning to finance, the goal is not to substitute what existing model can do. It is to exceed the accuracy of traditional model. So therefore, that is a good application of machine learning. And finally, recession. Recession is arguably not reflexive, although some might argue they are. Well, to us, we can regard recession as not reflexive, because if we suppose that there's a recession coming in next year and we short the stock, it is unlikely that the real economy will necessarily respond to you shorting the stock or many other people shorting the stock. Just because the stock market crash may not be enough to drive the economy into recession. Because recession, the real economy depends on a lot more than the financial market, although that appeared to be not the case in 2008. So I'll leave this as the open question, whether macroeconomic prediction is reflexive. I guess George Soros will think that it's not. It is reflexive, but to me, it's not so clear cut that a financial prediction can actually drive the real economy. This is an open question. Okay, so anyway, so supposing, however, that you are ambitious and you do want to predict returns, directly, well, there are still some considerations you have to look into. What time horizon do you want to predict? Would it be 1 second ahead, 1 minute ahead, 1 day ahead, 1 week, 1 month, or one quarter ahead? Right? What horizon? Which horizon can be predicted with the highest accuracy? For example, which horizon? But accuracy may not be everything you care about, right? May not be all that you care about. You might decide that even though predicting a 1 minute return, it has lower accuracy, but because you can make so many predictions, the opportunity to generate profit may be much more than if you can only predict once a year, even if your annual prediction is more accurate, right? So there's all this consideration that you have to pick what target variable you want, even if it's going to be return. And then also you have to decide if you want to predict sign or magnitude as well. Okay, so there is actually a question, interesting question, is Fed rates reflexive? Can we, through arbitrage activities, affect the Fed decision? And the questioner said he guessed not, and I would agree. It's unlikely that the Fed will look at. The Fed has explicitly stated that they do not use the stock market as the primary indicator of whether they should raise rate or not. It's not that they will completely pay no attention, right? But that's not their primary job. It's not to pop up the market. The primary job is to keep inflation in check and to keep employment at a decent level. It's not to keep the stock market up. So I would say that the degree of reflexivity is going to be low. And again, of course, it's not a 0 or 1 dichotomy. There are variables, there are target variables that are of varying degree of reflexivity. And obviously, I think weather is the least reflexive, right? But recession might be more reflexive than medium reflexive, I guess, and Fed rates might also be medium reflexive. Okay, all right. So so we dealt with the first step, picking your variable wisely. The second step, as I said, is to create a benchmark and baseline strategy. Now, a lot of people who are, again, from outside the financial field, but who are in machine learning, who are in data science, they're familiar with data science in other fields, would come to finance and say, oh, okay, well, you want to predict the sign of return, right? So what's the benchmark? As long as I can predict the sign of the return better than 50%, this model is good, right? Because 50% is obviously random. You just forward dice. You can predict accurately the return by 50%, the sign of return at 50% accuracy. So as long as you beat that, wouldn't you be happy about your machine learning model? Well, you shouldn't be, because again, I emphasize that the job of a machine learning algorithm in finance is not to be as good as a human trader, because the human trader is very bad in predicting market return or market direction. It is to beat the human trader. And the human trader typically already is better than 50%. Why? Because most return series exhibit either mean reversion or momentum. I have, in my first 2 books, I have discussed a lot about them, different strategies to take advantage of a mean reverting series and a momentum series. So there are already a lot of strategies that are useful if the return series exhibit one or the other. So the idea of machine learning is to not to beat the 50% benchmark, but to beat a mean reversion or momentum strategy benchmark, a simple mean reversion strategy or simple momentum strategy. For example, let's say you are trying to predict a 10-day return, the sign of a 10-day return. So, and you say, okay, this time series is, we can just compute the past 10-day return. And if the past 10-day return is positive, I would predict the future 10-day return is also positive. If you find that the return series is positively serially correlated, right? If there's momentum. Or if you find that the return series is anti-correlated, that is to say that this is mean reverting, the pi series is mean reverting, right? That pi series mean reverting means that the return series is anti-correlated. So if that's the case, then you would say, well, if the past 10-day return is positive, I would expect the next 10-day return will be negative. And that would already be a better than 50%, you will get an accuracy of better than 50% by this extremely simple trading strategy. So it is no point if you come up with a machine learning model that can predict as well as this naive model. We are not interested in that. We want to be doing better than that, right? Now, but of course, you can keep, thinking along this same line of, you can increase your sophistication of this strategy, right? You don't have to stay with this most basic of manual strategy. You can, for example, apply ARIMA, the classical econometric time series model, and apply that to a time series and fit that in the training set and let it spit out return prediction. A lot of academic studies have actually found that most machine learning models which uses price alone, right, that use only price and returns alone, are unable to outperform classical econometric models. It is quite shocking. no matter how complicated you are, it's just not able to outperform a classic econometric time series model such as a RIMA. So that is actually a fairly high bar to overcome, right? To outperform in the RIMA model is no simple matter. Also, you have to think about, well, some people would regard a linear or logistic regression with a single predictor. They don't even regard that as machine learning. But let's say that is another manual strategy, because anybody who doesn't even know about machine learning, or any classical statistician know how to use linear or logistic regression. So obviously your machine learning model has to outperform that also. And that again is no simple matter. To outperform a logistic regression model is no simple matter. Even if you use the most sophisticated neural network. So you better use that as a benchmark to beat, because otherwise, all this sophistication is quite a waste of time. Let me see. There's a question here. It says, can machine learning determine accurately if a time series is trending or mean reverting? Yes, it can, right? It can. But the problem is, can it beat the simple model, right? It is not that the machine learning algorithm cannot detect trending or mean reverting. It can. I have tried, and it does do that. But the problem is it able to significantly outperform a simple mean reversion and momentum model? And most of the machine learning model cannot. Okay, so it's not simple math. Just as it cannot outperform a classical econometric model, and it cannot outperform a simple logistic or linear regression model, right? So supposing that it can beat all that, right, your machine learning model, well, there are still more and more challenging baseline model that it had to overcome. For example, can it beat a linear logistic regression model with L1 regularization? Now, let me ask a question. Who can tell me what L1 regularization is? Yeah, okay. Yes, that is correct. There's an answer that says whether it's a penalty on the regression coefficients. In particular, L1 regularization means that you are going to add up the sum of the absolute value of the regression coefficients. The sum of the absolute value of the regression coefficient. L1 means that it is a well, what's the mathematical term? Norm of order 1, right? So you're taking absolute value is like taking it to the power of 1. And L2 regularization, by the way, is taking it to power 2. So you'd be taking the sum of the square of the regression coefficient in an L2 regularization. But in L1, you're taking only the absolute sum of the absolute value. L1 regularization is typically used in any machine learning algorithm, not just in logistic regression, but in any machine learning algorithm, to serve as a penalty term. It means that typically you would benefit. This penalty term penalizes the case where you have too many non-zero regression coefficient. You want to get rid of some insignificant regression coefficient. That is to say, you want to get rid of some insignificant features. That is what regularization means in general. And L1 regularization accomplishes it by penalizing the sum of the absolute value of the regression coefficient, so that your model it doesn't get too complicated. It doesn't use too many regressors, right? So that's a very favored feature selection method in machine learning to get rid of those spurious features to avoid overfitting. Okay, so that's, some people would already regard that as machine learning, but again, any statistician would know about linear and logistic regression with L1 regularization. Another term for it is lasso regression, LASSO. But again, this is what some people call shallow machine learning, right? This is borderline machine learning, but it is actually what some people would call shallow machine learning, because it's very simple, just linearly, combine things linearly with penalty. Now, do not laugh at this kind of simple methods. Again, as I said, first of all, it's very hard to beat them. You might think, wow, linear regression, anybody can do it. Are you saying that that's the best we can do in trading? Why can't I throw a 100-layer neural network at it? Must do better, right? Well, it turns out it is very hard to beat. And in fact, the conventional wisdom at this current stage is that the best predictive performance of a machine learning system is a combination of shallow and deep learning. There is a place for deep learning, but it cannot completely replace shallow learning, such as lasso regression. And that is opinion that is given by Francois Chollet. Question: anyone know who Francois Chollet is? Well, he is the creator of the Keras framework for deep learning. I mean, Keras is a sort of a easy to use framework to that you can apply to TensorFlow, and it's a basically a deep learning framework written in Python. So he's a Google deep learning researcher, and he wrote a book, and it's extremely good book, by the way, if you want to look it up. If you want to Google it, it's although it really is a tutorial on how to use Keras for deep learning, but what actually it does is that it gives you so many tidbits about good practices, best practices in machine learning that just go beyond deep learning, right? Even if you're not going to do deep learning, I think it's still beneficial to read that book. Okay, so I think there's a question. Somebody asked, what is L2 regularization? I think I answered that earlier. L2 is penalizing the sum of the squared of the regression coefficient. Here's another question, a little bit deeper. Generally speaking, is L1 or L2 regularization more effective? In other words, by effective, I mean, would L1 or L2 regularization typically generate fewer features? That they're more, which one is more selective on feature? Which one will penalize the small coefficient stronger? Which one will give you a more parsimonious model? Which one will give you a simpler model? L1 or L2 regularization? Any guess? That is typically an interview question. If you ever want to interview for a machine learning job, that is likely to be on it. So it's a good thing to know the answer. Let me see if there's anybody answer. I'm unable to really see the question very well. Okay, yes, somebody answered 1. Yes, you are correct, Gage. L1 regularization typically is give you a more parsimonious model, and the result and the explanation for that typically can be viewed graphically. But the best explanation I have seen is given by Kevin Murphy's book on machine learning. So if you Google Kevin Murphy and look up his probabilistic machine learning, I think the book is called, has a very nice section on L1 versus L2 regularization. Okay, let me see what my time. Oh, half the time is gone, but I think I'm doing okay. So question, what areas of finance do you think machine learning has particularly advantages in beating the human baseline? As I said, the best areas that it has a chance to beat human baseline is when it's trying to predict things that are not returned, things that are not reflexive. For example, I've given many examples already, but for example, earnings surprises, analyst estimates, that sort of thing. It typically can do a pretty good job. It's just pretty poor in predicting returns because of reflexivity. What's deep learning in the finance field? Well, deep learning is a very general methodology, so it can be applied to anything. In particular, in finance, if you are, any of the problem that we are interested in, whether in predicting earnings surprise, or whether you are trying to predict weather, or whether you're trying to predict supply and demand for a particular product or whatnot, all of that can be can be dealt with by deep learning, right? So I mean, deep learning is simply just stacking a number of neural network together, and number of layers of neural network together, and it can have different architecture. It could be a dense network, it could be LSTM, it could be a convolution neural net, it can be you know, what is it, the generalized adversarial network. It could be whatever the architecture you can come up with, but you know, the specific architecture, you know, and no one can say one or the other is the best architecture. Unfortunately, so you just have to try them all. So deep learning is just like a tool. As I said, any high school student know how to do deep learning now if they are you know, minimally competent in Python. So you know, we are not going to impress anybody if we tell them that we know how to do deep learning, because a high school student can do it, right? We don't expect to impress anybody by saying that you know how to do deep learning in finance. So, okay, so does Francois approach work for markets or cat pictures? Francois is, well, you know, we don't want to elevate Francois to his approach, because he's just built a framework that makes it easy. He's, you know, it's just a tool to use TensorFlow, which is the underlying Google deep learning algorithm. And even Google cannot claim all the credit for many of the advances in deep learning. It's just a software tool. A lot of the deep learning training techniques and a lot of the network architecture and so on and so forth, regularization techniques are created by many other researchers. It's not created by Google itself. So you know, it's a massive effort from many academic and commercial researchers. So I wouldn't call that Francois' approach. It's just that he made it very easy for any high schooler, practically speaking, to run a deep learning experiment. So I don't know that it is also, you know, question is whether it can deal with reflexivity better. I don't think so. I don't think so. Reflexivity has nothing to do with what kind of machine learning method you use, whether it's deep learning or shallow learning. It is just the nature of financial market. And it does not even limit it to machine learning per se. If you have a quant strategy, you are suffering from reflexivity. If you are even a discretionary trader, you are going to suffer from reflexivity. It's just the nature of financial market, not what you use to make prediction. Okay, so in the financial domain, there's a question: can you give a real example of the machine learning model that are used by companies that are successful in the market? Well, I mean, many companies are, for example, able to use machine learning to do a very intelligent asset allocation. Risk management is a great area. As I said, real-time volatility, realized volatility is a very good. It's much easier to predict than return. So, and it's not reflexive. So machine learning can do a great job there. Machine learning can help any financial traders by giving them the basic ingredients. So even if you're a discretionary trader, so many people say, oh, machine learning, only quants can use it. I'm a discretionary trader. I can't, it's no use to me. That is actually the complete opposite of the case. If you are a discretionary trader, you want to have a lot of inputs, right? You want to know, is the Fed going to increase interest rate tomorrow? Is there going to be recession next year? Is the crude oil going to go up or down? Is the market going to be volatile tomorrow? All these questions are perfect for machine learning. The discretionary trader is the one that is going to decide whether to buy or sell. But this person, she needs inputs, right? The discretionary trader doesn't mean that it just make bets based on out of thin air or by throwing a coin. No, the discretionary trader take into many inputs, and in her mind, she will combine them in some intuitive way or a mental model and decide whether to buy or sell. But where do the inputs come? The inputs, what are these inputs? These inputs would be, as I said, things such as whether the Fed is going to increase interest rate and so forth, right? That's where the machine learning can provide a lot of value, because they would do a much better job in telling you the probability of interest rate increase than any analyst can. It can beat analysts for predicting whether the Fed is going to increase interest rate or whether there's going to be recession next year. So if you are a discretionary trader, it is actually a great tool to have machine learning generated inputs to your model, and so can a quant trader, right? I mean, quant trader typically has a model that takes many input, and they know exactly how to combine them to generate a trading decision. And those inputs maybe traditionally come from analyst estimates or some other way. Now those inputs can come from machine learning. So that's a very good use of machine learning. Machine learning does not need to predict the output, the return. Actually, machine learning might be best in creating the inputs to a quant trading model. And that's not something that people often think of. It is in creating the inputs that it might have the greatest value. So the question is, some traders are good at picking up a pricing pattern. Will this be picked up by deep learning or a machine learning model? Yes, I think so. Yeah, that can be. But as I said, the problem is that if you are a discretionary trader and you trade a pattern for some time, and then all of a sudden it works less and less, you will immediately stop doing that, right? But discretionary trader, the beauty is that it's very, very flexible. You can stop trading a pattern a certain way when you see that it stopped working. A machine learning model, on the other hand, needs a lot of data, and it takes a long time for it to adapt, typically, unless you have, in general, I mean, you can certainly tune it so that it responds faster. But generally speaking, it is very slow to adapt to changing environment, because essentially machine learning model needs stationary statistics. If your statistics is changing rapidly, you need a model for how the data change, and that's not easy to come up with. And certainly the machine learning model won't be able to easily come up with a dynamic model itself. Maybe somebody's working on it. I have not certainly searched all literature, but if you are able to come up with a machine learning model that is dynamic, that not only can just generate a label given a feature, but can create a nonlinear time-varying dynamics of the market, such as, oh, well, this pattern used to exist, but now it's getting worse and worse. Maybe we think that the instead of buy, we should be shorting because of this recent change. And then maybe a month later, oh, the pattern has resumed, so we now need to switch back. If the machine learning model can do that, then it should certainly have a chance of beating the discretionary trader. And I'm sure someone, somewhere, some firm is working on that category of machine learning model. Okay, so let's move on. So as I said, if you are insisting on predicting returns, right, then the machine learning model has to outperform all of the above plus manual quant strategy. Can it outperform a discretionary trader? Right, that's the whole point. If you can trade better than a machine learning model, you don't need a machine learning model. So the whole point of machine learning model is to help improve your trading strategy, not to compete with you, but to outperform you. And there is a technique, however, that it can actually directly address this problem. It's called meta labeling, and that is a term coined by Dr. Lopez de Prado in his recent book. And I'm sure since he was a keynote speaker at the last QuantCon, I'm sure that many of you are familiar with his book. But the notion of meta labeling is one way, actually the most obvious way, to position your methodology the right way, which is to improve on existing strategy, not to come up with a new strategy from scratch. Because if you're going to come up with strategy from scratch, it is really hard to beat existing quant models. But if you already have an existing model, whether it's created by a quant or a discretionary trader or whatnot, or a shallow machine learning model, you can improve on it. So then, by definition, if the machine learning model has any sort of accuracy, you are going to outperform the the base strategy. So meta labeling is one way of doing that. So there's a question about data engineering, and I'm going to spend the last part of this talk on this. Obviously, garbage in, garbage out. So in machine learning model, data integrity is very important. Obviously we don't want wrong data, noisy data, but that's trivial. There are a lot of times the data that we use to train the machine learning model contain retroactive revisions. And a simple example would be earning announcement dates. Many people, thought that I'm going to create a learning announcement model, and they look at maybe Yahoo Finance or some other data source, even like IBES, right, expensive data source. And they look at the earning announcement dates, and they use that to create their earnings model and feed it into the machine learning model to work, to learn. And that would be quite wrong, because all those earning announcement dates are revised. They are not point in time. Even the very expensive data do not contain point-in-time earning announcement. So that's a big caveat that you have to pay attention to. Another oftentimes overlooked problem is look-ahead bias in the features that actually incorporated future information. And then there are features that are not stationary. For example, some people, I have seen people that had features that contain price as features. It's quite shocking, because how can you use price to as features? Because price, let's say Apple, maybe Apple started trading at $1, now is at whatever, $800. I mean, you cannot use features that are not stationary, and that is a point that is also emphasized in Dr. Lopez de Prado's book. You need to fractionally differentiate any features that are not stationary. And as features synchronous, that's another subtlety that many naive data scientists overlook when they try to get into machine in finance, is that many times you think that, oh, well, as long as we're using closing price, we are all good, right? Well, it turns out that different instruments, their closing times are different. So if you're going to trade at the close, there are some closing prices that cannot be used because they won't be known at the time of your trading. Simple example, you cannot combine the closing price of stocks with the closing price of futures and options if you are trying to predict the close-to-close return, because the closing time of options is typically later than that of stocks, and the closing price of futures, some of them are earlier than the closing price of stocks, some of them are later. So it's going to be a mess if you are trying to use the closing price of all these instruments from different markets in order to predict a return that is based on the close of the same day. Right. So that's oftentimes some majorly overlooked problem. So let me go to a question. I'm going to ask a question. So the first point I actually mentioned, I don't think we need to worry about. And second point is rather trivial. Let me just focus on the third question. Can you use the fixed index on day T as a feature to trade the spider at the same day close of the spider? Right? On the same day, can you use the fixed index closing value as a part of the feature to decide if you want to buy or sell spider or at the stock market close? A lot of people say yes. And let me see. Okay, so most people think that you can. The answer is no, you can't, because the fixed index is based off on the SPX options prices, and SPX options close at 4:15 Eastern time. Right, the option market always closes, in 15 minutes later. So the fixed value is only known at 4:15. You can't use that to trade spider. Okay, so let me see if there's some questions that I can answer as well. So that's a question, a very general question. Can a single person build machine learning model, or it can only be done inside an organization? Yes, certainly a single person can do. I don't think that there's. I mean, it's not necessarily optimal, right, to work alone. I personally favor at least working with one other person on any project. I'm much more motivated and disciplined if and my quality of my work greatly improve if I work with someone. That's the notion of pair trading in software development. But that's the whole point of pair trading. I'm sorry, not pair programming. Pair programming in software development is a well-known practice, and it's always improve the quality of your work, and that's the true in data science as well. So I do recommend you pair up with someone good that you can work with. And but if necessary, there's no reason why you cannot do it alone. Anyone can do it on the desktop, and nowadays with all these cloud-based servers that you can use if you need a GPU, you don't even need to buy a GPU for deep learning, right? Example where a combination of deep and shallow learning. It's actually very simple ensemble method. Many machine learning model can be improved if you combine them linearly. So you just either combine their probabilities linearly, or you combine you implement a voting system so that use a majority vote or something. So there are many ways to combine them. Changes in stationarity non-reflexive. That's a good question. I have no idea. Changing in stationarity, no, I believe that's quite reflexive actually. Okay, so I believe that I can go on. Better finish off before answer more questions. Okay, so data engineering. Non-price data, a lot of time people want to use alternative data as part of the feature set, and it may be quite useful, but it is also more tricky to ascertain the quality. My advice is that it's better to extract those non-price data feature yourself than to rely on some third-party model. For example, many times people tell you the sentiment of a news item. Well, it's anybody's guess if their sentiment model is any good, right? So it is best, if you can, to use machine learning to train your own sentiment model. More data reduces variance. Okay. In machine learning, there's the dichotomy of bias versus variance. Bias means the prediction error in the training set, and variance means the prediction error in the test set. And naturally, we prefer that the error is low in the test set, right? That's what it really matters. But oftentimes, you are supposed to only tune the error in the training set, right? So it is a question of, okay, even outside of machine learning, in any quant model, there's a question of how much data is necessary to tune the model, to optimize the parameter. And generally speaking, the more data you have, the lower the variance. That is to say, the lower the prediction error in the test set. But it does increase the error in the training set if you have a lot of more and more data. So that's how much is enough? That is something that is actually very easily determined through the learning curve. The first question, actually, I've answered myself. The more data you have, the less variance, but it actually increases the bias. You will get an increasing error rate in the training data typically. And what is the learning curve? So anyone know what the learning curve is? It is a common technique in machine learning, this notion of learning curve. Anyone know what that is? Yes. Many of you know what it is. Let me show you. It is just simply the show you the error rate of either the training set and the test set, right? The error rate of the test set and the training set as a function of, in this case, the training set size. You can see that typically the larger the training set, the more data you have, the error on the training set actually increases. And meanwhile, the error rate on the test set decreases. So how much is enough is determined by where these two curves kind of intersect, right? So the or where they stop improving. So at some point, the test error doesn't decrease anymore, and you know that that's where you have enough data. So a learning curve is a very useful tool, not only for determining the optimal training set size, but it's also useful as a way to determine how many iterations, for example, you need to train the neural network, and many other hyperparameter tuning. Right? This is generally speaking a good hyperparameter tuning method because it not only shows you how tuning this parameter help with your training accuracy, but it also tells you how it helps you with the test set accuracy. Okay, so great. And more ideas about features engineering is that many people forgot that you are not restricted to using only raw data as features. You can transform them as in some fashion before you become features. And there are many kind of functions that you can apply to. You can take the differences, you can take the various signal processing transformation, you can take real time, transform them using a time series model and take their coefficients. You can fit them to a probability distribution and take the parameters of those distributions as features and so forth. And then you can conform them. You can take a composition of the function. Now, all these are important, but typically they are more important for shallow learning and also for random forest, this kind of feature engineering, than for deep learning. Anyone know why? Why is it that in deep learning it is less, feature engineering is less important, at least feature engineering in the form that I discussed? Yes, I think a lot of you realize that. Deep learning, the whole idea is that in a neural network, you have made a lot of functions of functions of functions, where you are combining the original features in nonlinear ways, combining them in a multiplicative way, and then transforming them in a nonlinear way. So there is a theorem in neural network, namely that it is a universal function approximator. Right? A neural network is a universal function approximator, meaning that it can practically approximate any nonlinear function that relate the input features to the output target. Therefore, it is not really necessary. It already does all this feature engineering for you in some sense as you go through layer after layers of transformation. That's why in deep learning, one of the advantages of deep learning over shallow learning is that the feature engineering is not as important. But if you are going to do shallow learning, you have to, it is quite helpful if it undergoes that kind of transformation manually before you feed it into the algorithm. Okay, so that's it for feature engineering. I think time is running out, so feature selection is a big topic, and we already mentioned one method, which is L1 regularization. So there are other ones, stepwise regression and mean decrease accuracy and so forth. And I'm not, going to, since these are actually much more related to machine learning itself rather than the things you do before machine learning, I will leave it for another time because this talk is focused on what you do before machine learning. So actually, I'm not going to emphasize that. So now you're ready to proceed to the machine learning problem after all these preliminary talks. And thank you very much for joining us. Let me take up a few questions further before we wrap up. Yes, There's a question about voting and combining that ensemble method. That is reinforcement learning. Yes, reinforcement learning, is that the kind of tool suited for dynamic strategies? That might be. A lot of people are interested in reinforcement learning and looking to see whether it's applicable to trading. I haven't done much research in that, although interestingly, one of the theses that I have advised in my role as a faculty at Northwestern was on using reinforcement learning applied to trading. Unfortunately, the result was not great. I'm sad to say, but that's just one thesis. So I'm sure someone somewhere else were able to do better. What is the best book for machine learning? I would say that well, in financial machine learning, you should certainly look up Dr. Lopez de Prado's book, and after that book, you can certainly look at Kevin Murphy's book on probabilistic machine learning, and you should look up Francois Cholet's books on deep learning in Python. That is basically the Kira's tutorial. And then, of course, you should look up Dr. Andrew Ng's, who is the founder of Coursera, in case you didn't know. That's his new book is called Machine Learning Yearning. It's very readable. There's practically no math in it, no code and no math. And that's certainly helpful to read. And let's see, where can we get data from machine learning models? Well, that's you can get data from Quanto and Quantopian and many other sources. Well, someone asked why price cannot be used as a feature. Obviously, price is non-stationary, right? So something that is not stationary means that it will not be the same. Apple is not going to go back to $1 anymore per share, I hope. If it goes back to $1, I think our economy will have collapsed already. So what is the point of training a machine learning model with a feature that will never again reappear? So does Python offer all the benefits of C++? I am going to be bold and say that there's nobody who uses C++ to do machine learning research. And I mean nobody. It's just I'm going to be bold in stating that. And what techniques can be used for identifying stationarity? Oh, that's a very basic technique that I discussed in my first book. For example, the ADF test, augmented Dickey-Fuller test. That is implemented in multiple packages: MATLAB, Python, R. They all have ADF tests, and I certainly have examples on how to do that in my first and second book. Okay, can co-integrated prices be used as a feature? Yes, co-integrated prices, if you combine them into a stationary time series, then it's stationary. So it can be used as a feature. As long as what you're feeding in as feature is stationary, that's good. So co-integrated price series, if you create a spread out of it, it's certainly stationary. So thank you very much.
Yep, great. Thank you so much, Ernie. That was awesome. Thank you, everyone, for joining.